Welcome to AWS Mastery Labs, turning AWS chaos into clarity with bite-sized tutorials, hands-on labs, and exam-smashing tips. In this video, we'll explore how to scale Amazon DynamoDB effectively to support high-performance, mission-critical applications. We'll break down the mechanics of partitioning, delve into adaptive capacity and on-demand scaling, and understand how DynamoDB handles massive workloads without compromising on speed or reliability. Let's get started. Amazon DynamoDB is a fully managed NoSQL database service designed for applications requiring low latency, high throughput access to data. It supports both key-value and document-based data models, making it versatile for a wide range of workloads. Built for seamless scalability, DynamoDB automatically distributes data across multiple partitions based on a hashed partition key, allowing it to handle millions of requests per second without manual sharding. By default, DynamoDB provides eventual consistency, but applications can opt for strongly consistent reads when needed. It also supports ACID transactions, enabling multi-item, multi-table operations with transactional guarantees. The service offers two pricing models: on-demand mode, which automatically scales throughput as needed, and provisioned capacity mode, where developers can allocate read and write capacity based on the workload to optimize costs. To enhance query flexibility, DynamoDB supports global secondary indexes, GSIs, and local secondary indexes, LSIs, allowing applications to efficiently retrieve data using alternative access patterns. Additionally, DynamoDB streams capture real-time changes to table data, enabling event-driven architectures by integrating with AWS Lambda, Amazon Kinesis, or other services for change data capture, CDC, auditing, and analytics. Security is a core aspect of DynamoDB, with built-in AWS Identity and Access Management integration, encryption at rest using AWS KMS, VPC endpoints, and CloudTrail logging for auditability. It also complies with industry standards such as SOC, HIPAA, PCI DSS, and FedRAMP, making it suitable for highly regulated environments. Overall, DynamoDB is a powerful solution for applications requiring millisecond latency, automatic scaling, and seamless integration with AWS services, making it a preferred choice for high-performance workloads such as gaming, IoT, e-commerce, and real-time analytics. Now, in this illustration, we see how the design for a product catalog table, modeled for a NoSQL database like DynamoDB. Instead of breaking up the data across multiple normalized tables like traditional RDBMS, here we use a single table design that consolidates all product information, regardless of type, into individual items within one table. The table uses a composite primary key, where the partition key is the product type, such as book, album, or movie, and the sort key is the product ID. This allows for logical grouping of items by type while maintaining uniqueness across all products. What's most interesting about this design is that each product's metadata, whether it's ISBN and publisher for a book, or artist and track list for an album, is stored directly within the same item as the core product attributes. Even the tracks for an album can be embedded as a list of nested documents within the album item itself. This is possible because DynamoDB supports a flexible schema. Each item can have a different set of attributes, tailored specifically to the product type it represents. By flattening the data and storing it in a denormalized format, this design is optimized for high-performance, single-table queries. You can fetch a complete product record, including all its details, in one request with no joins, which is a major advantage for read-heavy, latency-sensitive applications. In provisioned capacity mode, DynamoDB allows you to define in advance the number of read capacity units, RCUs, and write capacity units, WCUs, that a table or index should support. This means you're explicitly setting the throughput the system is expected to handle, and your build based on the capacity provisioned, whether or not it is fully consumed. This model is particularly advantageous when you have a good understanding of your application's workload patterns and can estimate traffic volume ahead of time. To help balance performance and cost efficiency, auto-scaling can be enabled within provisioned mode. This feature monitors the utilization of your table and automatically increases or decreases the provisioned throughput based on defined thresholds and actual usage. It ensures that your application remains performant during sudden traffic spikes while scaling down during low activity periods to save costs. Despite auto-scaling, you still have fine-grained control over minimum and maximum capacity settings, providing predictability and cost management. One of the major benefits of this mode is cost predictability. Because you allocate capacity upfront, your monthly billing remains stable and consistent, making it easier to budget for DynamoDB usage, an important consideration for production systems with strict financial oversight. Provisioned capacity mode is best suited for workloads with consistent or predictable access patterns, such as internal enterprise systems, scheduled batch jobs, or well-modeled APIs with steady traffic. However, it's important to note that this mode comes with certain scaling limitations. There's a finite rate at which provisioned capacity can be adjusted per minute, and if your application exceeds the configured limits, DynamoDB will throttle requests, leading to increased latencies or failed operations until the demand subsides, or the provisioned limits are raised. In on-demand capacity mode, DynamoDB takes a fully automated approach to scaling. It dynamically adjusts throughput in real time to meet your application's demands, without requiring any manual configuration or capacity planning. As traffic fluctuates, whether it surges or drops, DynamoDB seamlessly scales to match it, ensuring consistent performance and eliminating the risk of throttling due to under-provisioning. This model is particularly well suited for applications with unpredictable or spiky workloads, where traffic patterns are hard to forecast or can vary widely throughout the day. Because you're billed only for the actual read and write requests made, on-demand offers strong cost efficiency for workloads that aren't consistently high in volume. This makes it ideal for new applications, prototypes, startups, or any scenario where traffic patterns are still evolving or difficult to predict. One of the biggest advantages of on-demand is the elimination of capacity planning. Developers don't need to estimate future throughput or monitor scaling thresholds. DynamoDB handles it all behind the scenes. This makes it a hands-off solution, perfect for teams that prefer operational simplicity and need the flexibility to grow or shrink with minimal overhead. However, for applications with steady and predictable workloads, the cost structure of on-demand can sometimes be less economical than provisioned capacity. Since you pay per request, high-volume steady-state workloads might accrue higher charges compared to a well-tuned provisioned setup. When using provisioned capacity mode in DynamoDB, you need to allocate a specific amount of read and write throughput to your tables up front. This is done using a system of capacity units, CU, essentially a budgeting model for how much read and write traffic your application can perform per second. First, we have read capacity units, RCUs. RCUs are based on the size of the data being read. Each RCU allows you to perform one strongly consistent read per second for an item up to 4 kilobytes in size. If you opt for eventually consistent reads, which return data with slightly relaxed consistency guarantees, you get double the throughput. That is, one RCU supports 2 eventually consistent reads per second. For transactional reads, which ensure full ACID compliance, the cost is higher. Each transactional read consumes 2 RCUs per item per second. On the right side, we use write capacity units, WCUs. Writes are billed based on 1 kilobyte of data per item. So 1 WCU allows you to write a 1 kilobyte item to the table once per second. Larger items are rounded up to the nearest kilobyte. And just like with reads, transactional writes, which are atomic and isolated, require double the capacity. 2 WCUs for 1 transactional write per second. It's important to note that all reads and writes in provisioned mode are metered. If your application exceeds the allocated throughput, DynamoDB may throttle requests, unless you've configured auto-scaling to adjust the capacity dynamically. This capacity-based model gives you predictable performance and cost, especially if your application has stable and well-understood traffic patterns. However, it does require thoughtful planning to balance performance, efficiency, and budget. When operating in on-demand capacity mode, DynamoDB offers a flexible and automatic scaling model. You don't need to pre-allocate capacity. Instead, you're billed based on the number of requests your application makes, using request units, RU, as the unit of measurement. In this mode, the system intelligently adjusts throughput based on demand, making it ideal for unpredictable or spiky traffic patterns. Let's look at how it works, starting with read request units, RRUs. Each RRU supports one strongly consistent read request per second for an item up to 4 kilobytes in size. For eventually consistent reads, which allow for slight delays in data propagation, each RRU can handle 2 requests per second, effectively doubling your read efficiency. And for transactional reads, which ensure ACID compliance, you'll need 2 RRUs to support a single read request per second. On the right side, DynamoDB uses write request units, WRUs, also calculated in blocks of 1 kilobyte, rounded up. One WRU supports one standard write request per second. If you're performing transactional writes, the cost doubles. You'll need 2 WRUs per write per second. Unlike provisioned mode, there's no need to manage or forecast capacity. DynamoDB automatically scales to accommodate your workload in real time. This simplicity is a major advantage for teams that want agility without operational overhead. However, this flexibility comes with a trade-off. On-demand mode may be more expensive than provisioned capacity for applications with consistent, predictable traffic. But for variable workloads, new apps, or sporadic spikes, it's the perfect fit. You get performance when you need it, and you only pay for what you use. Let's now walk through a practical example to understand how read and write capacity units, or RCUs and WCUs, are calculated in DynamoDB's provisioned capacity mode. To make this concrete, we'll base our calculations on a single item that's 3 kilobytes in size. DynamoDB measures reads and writes in specific block sizes, 4 kilobytes for reads and 1 kilobyte for writes. So it's important to understand how your item size impacts your capacity consumption. By following along the calculations, you will arrive at the following capacity: 1 RCU for a standard read, 1 RCU for an eventually consistent read, 2 RCUs for a transactional read, 3 WCUs for a standard write, and 6 WCUs for a transactional write. Understanding these calculations is critical for optimizing your DynamoDB cost and performance. It helps you estimate usage accurately and avoid unnecessary throttling or over-provisioning. Now let's flip the perspective and calculate how much throughput you can achieve if you've provisioned your DynamoDB table with 10 RCUs and 10 WCUs. This kind of calculation is useful when you want to understand the data volume your table can handle per second based on your current capacity settings. Remember that DynamoDB measures reads and writes in specific block sizes, 4 kilobytes for reads and 1 kilobyte for writes. By following along the calculations, you will arrive at the following throughput: RCUs with strong consistency, 40 kilobytes per second. RCUs with eventual consistency, 80 kilobytes per second. RCUs with transactional read, 20 kilobytes per second. WCUs, 10 kilobytes per second. WCUs for transactional write, 5 kilobytes per second. This exercise illustrates how your provisioned capacity translates into actual data throughput, helping you right-size your table based on performance needs and workload characteristics. In DynamoDB, partitions serve as the fundamental storage and processing units, enabling the system to scale horizontally while maintaining high availability. Each partition is a distinct segment of underlying storage and is responsible for managing a portion of the table's data and request traffic. DynamoDB automatically distributes data across multiple partitions to optimize performance and scalability. A key factor in partition management is the partition key, also known as the hash key, which determines how data is distributed. Items that share the same partition key are stored within the same partition, ensuring efficient retrieval. As the dataset grows or demand for throughput increases, DynamoDB dynamically creates and manages partitions without requiring manual intervention. Each partition has specific size and throughput limits. A single partition can store up to 10 gigabytes of data and support up to 3,000 read capacity units, RCUs, and 1,000 write capacity units, WCUs, in provisioned mode. When these limits are exceeded, DynamoDB splits partitions and redistributes the data to maintain optimal performance. However, if access patterns are uneven, where a small set of partition keys receive a disproportionately high number of requests, a hot partition may form, leading to throttling and degraded performance. To prevent this, careful partition key design is necessary to ensure even data distribution across multiple partitions. In provision capacity mode, the total allocated read and write throughput is distributed across all partitions, meaning that a sudden increase in throughput demand may cause DynamoDB to add new partitions to accommodate the load. Conversely, in on-demand mode, DynamoDB automatically adjusts partitioning and scaling based on traffic patterns, removing the need for manual capacity planning. While partitions are abstracted from direct user management, their behavior can still impact application performance. To monitor partition-related issues, AWS provides Amazon CloudWatch metrics and DynamoDB performance insights, which help identify bottlenecks caused by inefficient key design or unexpected traffic spikes. Understanding how partitions function is crucial for designing a scalable and efficient DynamoDB schema that ensures balanced workloads and optimal system performance. Let's begin with a simple example to illustrate the foundational structure of a DynamoDB table and set the stage for understanding partitioning. In this illustration, we have a product catalog table that holds information about various items available for sale. The table uses a simple primary key, a single attribute called ID, which uniquely identifies each product. This means DynamoDB uses the ID value as the partition key, determining how the data is distributed across storage partitions. Alongside the ID, the table includes additional attributes like category, name, price, and attributes. These provide relevant information about each product. For example, what type of item it is, how much it costs, and any custom metadata such as size, color, or specifications. Now that we've seen the basic structure of our product catalog table, let's take a closer look at how DynamoDB distributes data across partitions using the partition key. In this case, the ID. In this illustration, we have 5 product items, each with a unique ID value. When these items are written to DynamoDB, they are not stored in any specific order based on their ID values. Instead, DynamoDB uses a hash function to map each ID to a partition. The output of this hash function determines which physical storage partition will store the item. As shown, these 5 items are spread across 3 different partitions. Some partitions may hold multiple items, while others may have fewer. It all depends on how the hash values distribute the data. This unordered hash-based indexing ensures even data distribution across partitions and supports DynamoDB's ability to scale horizontally. It's important to note that because the distribution is driven purely by the hash of the partition key, the order of insertion or the natural order of IDs is not preserved. In the second part of our example, we've made a strategic change to the table design. Instead of using ID as the sole primary key, we've now defined a composite primary key where category becomes the partition key and ID is the sort key. So why make this change? In the previous structure, using only ID as the partition key meant that each item was isolated, making it efficient for single item lookups, but limiting for grouped access patterns. By switching to category as the partition key, we can now logically group products by category into the same partition. The ID then acts as the sort key, which allows us to query items within a category in a defined order. For instance, by ascending ID, or even by additional filtering on other attributes. This design supports more flexible and efficient queries, such as, give me all products in the books category. Return the top 5 most recent items in electronics. Category. Fetch items between certain ID ranges within a particular category. Under the hood, DynamoDB will now place all items with the same category into the same logical partition and internally organize them by ID. This enables fast, indexed lookups and range queries, improving both performance and scalability for such grouped access needs. This change reflects a best practice in DynamoDB data modeling, designing your keys based on how your application queries the data, not just how it's structured. In this updated illustration, we revisit the same 5 product entries from our catalog, but this time we visualize how they are distributed and organized after altering the primary key structure to use category as the partition key and ID as the sort key. What you'll notice here is that items are now grouped by their category, meaning all products belonging to the same category are stored within the same logical partition in DynamoDB. For example, all items labeled as books will fall under the same partition key, books. Within each partition, the items are then ordered by the ID, thanks to the sort key. This visual reinforces the importance of choosing the right keys based on your access patterns. Now let's walk through how DynamoDB calculates the number of partitions for a table based on its size and provision throughput. In our example, we have a table that is 8 gigabytes in size, with a provisioned capacity of 5,000 read capacity units, RCU, and 500 write capacity units, WCU. DynamoDB uses three main factors to determine the number of partitions. Table size. Each partition can store up to 10 gigabytes of data. Read throughput. Each partition can support up to 3,000 RCUs. Write throughput. Each partition can support up to 1,000 WCUs. By following the calculations, you will see that the highest of these three numbers is used by DynamoDB to determine the final partition count. In our case, that rounded value is 3. Assuming a uniform spread of data and traffic across all three partitions in our DynamoDB table, each partition holds approximately 3.34 gigabytes of data. In addition, each partition has approximately 1,667 RCUs and 167 WCUs. Each partition is responsible for a manageable portion of the overall workload, both in terms of storage and throughput. This partitioning logic is crucial because it directly affects data distribution, performance, and scalability. Properly understanding how your table's size and throughput influence partition count helps you design more efficient schemas and avoid issues like hot partitions or throttling. In this illustration, we examine how DynamoDB partitions evolve as data grows over time, a key aspect of scaling behind the scenes. We begin with a table that stores 25 gigabytes of data, initially spread across three partitions. Alongside that, we have provisioned capacity of 3,000 read capacity units, RCUs, and 1,000 write capacity units, WCUs. Each partition has approximately 1,000 RCUs and 334 WCUs. We can use the calculation from the previous slide to arrive at the results. As the table size increases from 25 gigabytes to 45 gigabytes, DynamoDB responds by splitting the data across 5 partitions. This automatic scaling is triggered because a single partition can only handle up to 10 gigabytes of storage, and the original 3 partitions would exceed their combined 30 gigabytes limit with this new data size. By expanding to 5 partitions, DynamoDB ensures that each partition now holds approximately 9 gigabytes of data, staying well within the system's storage thresholds. Importantly, this repartitioning maintains optimal read and write performance. The provisioned throughput units are now distributed more evenly across the 5 partitions, giving each one 600 RCUs and 200 WCUs. This part of the illustration reinforces the point that data volume directly influences partition count, and that DynamoDB automatically handles this under the hood to scale seamlessly as your application grows. Adaptive capacity is a built-in feature of Amazon DynamoDB that helps manage uneven access patterns by dynamically redistributing throughput capacity across partitions. In real-world applications, certain items or partitions may receive significantly more traffic than others, resulting in what's known as a hot partition. Adaptive capacity addresses this by automatically detecting these hotspots and shifting additional capacity to the partitions or even specific items that need it, thereby reducing the risk of throttling without any manual intervention. One of the standout features of adaptive capacity is its fine-grained operation. It doesn't just rebalance throughput at the partition level, but can also make adjustments at the subpartition or item level, targeting frequently accessed keys directly. This ensures more efficient use of provisioned capacity, especially for workloads with naturally skewed access patterns. In provision mode, adaptive capacity plays a crucial role in enabling consistent performance without over-provisioning the entire table. Instead of developers having to guess and allocate excess throughput to handle potential spikes, DynamoDB dynamically and intelligently reallocates it where it's actually needed. This results in optimized resource usage and cost savings. Moreover, adaptive capacity isn't limited to base tables. It also supports local and global secondary indexes, LSIs, and GSIs, ensuring performance benefits across all access paths. It reacts in near real time to shifting traffic patterns, which is especially beneficial for applications with fluctuating or unpredictable workloads. Perhaps best of all, adaptive capacity is enabled by default and incurs no additional cost. making it an integral, cost-effective part of DynamoDB's architecture. However, while it provides a safety net, it should not replace good partition key design. A well-distributed key strategy is still fundamental to achieving optimal performance and fully leveraging DynamoDB's scalability features. This illustration brings together two key features of DynamoDB's scalability model, auto-scaling and adaptive capacity, and shows how they work in tandem to handle workload variations across partitions. Let's first look at adaptive capacity in action. In this scenario, partition 2 is experiencing a surge in traffic, making it a hot partition. Under normal conditions, each partition gets an equal share of the provisioned throughput. However, DynamoDB automatically detects that partition 2 is under pressure and dynamically reallocates any unused capacity from the cooler partitions, such as partition 1 and partition 3, to partition 2. This intelligent rebalancing happens without requiring manual intervention or a change in the total provisioned capacity, helping prevent throttling and maintaining consistent performance. Now let's consider auto-scaling. In the background, DynamoDB's auto-scaling monitors the overall throughput consumption using CloudWatch metrics. Based on the thresholds we've configured, in this case, a trigger to add 2,000 read capacity units, RCUs, and 500 write capacity units, WUs, the system begins the process of scaling up the table's capacity when it detects sustained high utilization. This ensures the table as a whole can handle increased demand over time, not just temporarily shift capacity between partitions. Together, adaptive capacity provides fine-grained responsiveness at the partition level, while auto-scaling ensures long-term elasticity at the table level, creating a powerful combination that supports both performance and cost efficiency in real-world workloads. Bursting in DynamoDB refers to its ability to temporarily accommodate traffic spikes by using unused throughput capacity. This feature is particularly applicable in provisioned mode, where read and write capacity is pre-allocated. If a table or a partition consumes less than its allocated capacity, DynamoDB accumulates unused capacity as burst credits for a limited time, up to 5 minutes. These credits can then be used to handle sudden surges in traffic, allowing short-term scalability without immediate throttling. This mechanism is especially useful for applications with predictable but infrequent spikes, such as login events, periodic data synchronization, or promotional campaigns. However, it's important to note that bursting happens at the partition level. So if a specific partition becomes hot and hasn't accumulated enough burst credits, throttling may still occur, even if the overall table has unused capacity. This reinforces the importance of good partition key design to distribute traffic evenly across all partitions. Unlike provisioned mode, on-demand mode does not rely on burst credits. Instead, DynamoDB automatically scales to match the request rate, making it ideal for applications with highly variable or unpredictable workloads. However, bursting provides a valuable buffer for provisioned tables, enabling them to absorb short-lived spikes without requiring over-provisioning. To take full advantage of bursting, it's crucial to monitor usage using tools like Amazon CloudWatch, which can expose metrics such as consumed read capacity units and throttled requests. These insights help teams understand how burst capacity is being utilized and when adjustments to provisioned throughput might be necessary. Thank you for joining us in this video. If you haven't already, we'd love for you to subscribe to our channel to stay updated with our latest content. We look forward to sharing more insights with you in another video. Until then, keep exploring. And thank you for watching.